Assalamu alaikum everyone. Today we are going to conduct lecture number 23 of our this course Microprocessor and Assembly Language, and today's topic is logical instruction. Okay, in this lecture we are going to cover four different instructions, and these are very similar to logical gates. They are also very well known logical gates, so I hope explanation of these instructions would be very easy for me because you have already certain developed understanding, and we will be focusing more towards instructions, criteria, and how different bits of the various registers and memory operands are going to modified when these instructions will affect them. Okay, we will be covering four instructions, and this is our first instruction, which is AND, AND, and it is for logical AND, which we know that it is very important gate, and the format is very simple and very easy to understand. A and D and D comma S. D is here destination operand, which means the result holding register, or the affecting result affecting register. Okay, and second operand is S. S is source operand. So of course we know that whenever we are going to perform and we need two different bits, so a bit will be taken from destination operand and a bit will be taken from source operand. Yes, it is a bitwise command, so it if one is interested to examine the effect of these instructions, he or she has to look at the content in the binary level or the bit level. Okay, what is going to happen in the operation? It's quite simple. Source dot D, that means it is going to be AND. Both of these destination and source bits will be going to AND, and the result will be storing in the destination operand. Okay, as it is similar to, it is an instruction, and so similarly likewise every instruction and instruction will also affect certain flag register, and those are those are shown here in this last column. So there are various flags, and there are some flag status bits which are not going to affect, so these are also mentioned here. Okay, second instruction is very important instruction, or very important logical gate, that is OR, or inclusive OR. It is normally known as OR, but its official name is inclusive OR. So it is for logical inclusive OR gate, and operation or the format is very simple: OR D comma S, and it is also a bit level command. Since we are talking about logics, so logic is always performed on bit level. So D is a destination operand and S is a source operand. So plus is normal sign for OR gate, and it's very well known notification. So source plus destination, and result will get stored in destination. Okay, there are some flags which will get effects, and some are undefined, so those are mentioned here. Okay, number third instruction is exclusive or XOR. So its format is exclusive OR D comma S, and like I explained in last two instructions, this is very simple, and this is going to be in bit level, and we will be exploring them using emulator example. So source plus exclusive OR, this is exclusive OR instruction, and destination and result will be storing in the destination. Again, the affecting and non-affecting flags are mentioned here in last column. Okay, the fourth instruction that we are going to see in this lecture is NOT, and or the logical NOT. So we know that logical NOT gate is always applicable only on one operand. So NOT D will be its format, and D is destination. So effect and input to the instruction will be same as the destination operand. So D will be complemented or not, and result will again store in the D operand, and there will be no flags which can get effect, so that is why none is written here. So these are the four instructions we are going to see in this lecture. So let's proceed to the emulator practice. Okay, let's start our emulator practice for AND instruction. So we will be testing emulator for AND instruction. So let's say we are going to perform AND operation, and I hope if you remember what is AND gate. So let's say we are performing AND between 0 and 1, so result would actually cause what it will cause 1. But remember, we are playing with 16-bit register or 8-bit register, so it will be affecting the complete register. So what is going to happen, let's say we have certain information stored in certain register, for example move al comma 5 f. Okay, I've just used 8-bit register, and then a next register could be cl. Cl is basically holding information e9 hex, and e is in number, okay, e is an alphabet, so we will be using up 0 prefix in this manner. Okay, let me delete that. Okay, yes, now we are going to perform what AND instruction. So AND al comma cl, so we will be actually ANDing cl and al. So before we go and execute this program, let's do it manually. So al content is what? Al content is 5f in hex, and if I convert it into binary, it will become 0101 and 111. I hope you know it. It is binary data. And then we will be playing with cl, so let's do the same thing for cl. Cl data is e9, so it is in hex, and we will be converting it into binary, so it will become what? It will become 110 and 1001. Okay, so now we know that it is AND gate, and we have to play with bit level. So we will be performing bitwise AND. So 01 would become what? 1, 11 would become what? 1, 10 becomes 0. Okay, 01 was 0, I'm sorry, 10 was 0, 1 would become 1, 0 and 0 and 1. I hope this thing is clear to everyone. Okay, and so that would be our result. And let's, if we convert it into into hexadecimal, so it would become what? 0100 would become 4, and 1001 would come 9. So that is our expected result in hexadecimal. So let's comment it. Yes, and now we are going to emulate it. Okay, it is okay. Now we are performing our instruction 1, which says 5f is moved. Yes, it is correct. Next instruction, e9 is moved in cl. Okay, that is also correct. Now we are going to perform what? AND al comma cl, and in this particular operation al will be destination and it will be modified. So let's see, single step. Yes, 49. I hope you can see the result. And that's how. And similarly, in the same approach, you can use a 16-bit register, and you can perform this bit level instruction, this bit level logical instruction, which is AND. I hope this point is clear. Okay, we will try to examine our logical gate OR. So in this slide I will be modifying the previous content. OR instruction we are going to use a similar data, but actual difference will be here. The operation is OR instead of AND. So let's see what is going to happen here. So 01, you know, it will cause 1. If you don't remember, I can just recall it for you. In OR gate, what happened actually, you can okay, let me just set it. Yes, yeah, over here. Yes, so in OR gate, what happened, you have to check if any of the input is high, then result will be high. So 01, so there will be 1, 1 1, and since both are high, so it will high. 01 it will be 1, and 01 it will be 1, 1 1 1 0 and 1 and 1. Sorry, it is a 1. Yes, So that's it. So if we convert it into hexadecimal, it will become what? It will become FF. Okay, I hope this point is clear. So let's do this program practice. Press the emulate button. Step 1, 5F is loaded. Step 2, E9 is loaded, and since we are going to use this AL register as destination operand, so it will be modified and result will be what? FF. Let's see. I'm sorry, I did not change this AND command, so I forgot it. Let's change it, or, and let's rerun it. Evaluate. Okay, single step. 5F is loaded. E9 is loaded. And look, the result is FF. I hope you can see it. So I hope this point is clear. Just to modify and just to bit more practice, we can change the destination operand. Let's say we do it, we use BL here, and we use CL as destination operand, and we choose some other, make some 0. Both inputs are 0. For example, this case, if it is 0, so it would become what? Not 5, rather 4, so it will be 4. I'm just changing few data, and rest of the operation would be true, so it would be 0 0 0, and it will become EF. So I'm going to change the register, I'm going to change the destination operand, I'm going to change the input. So let's see what is going to happen. Evaluate. It is just for the practice purpose, nothing more than that. Okay, so let's evaluate. Single step. 4F is loaded, which was supposed to be in BL. Yes, it is correct. E9 is loaded, and it was supposed to be in CL, and this time CL is our destination. We are performing OR gate. So let's see. Look, EF, it is the content of CL, or the destination operand, as we were expecting. I hope this point is clear. Okay, in this slide we are going to examine XOR instruction. So let's take to 16-bit number this time, because in the last example we discussed to 8-bit numbers. So in this example we are going to discuss some 16-bit number. So move AX. Okay, move AX, comma, let's say 1 2 3 4 hex is loaded in AX, and move, this time I'm using DX, and let's say it is 0F87 hex. Okay, I believe it is a 16-bit number, and we are performing exclusive OR here, and this time we are using DX as a destination and AX is a source operand. So I'm going to do it manually first. So AX value is what? 1 2 3 4 hex, and it is basically, if I'm okay, let me put it on the left side. Yes, okay, here and here. Okay, yes. So I'm going to convert into binary. It would be 0 0 1. Remember, it's hexadecimal. 2, it would become 0 1 0. 3, it becomes 0 0 1 1. 4, it will become 0 1 0 0. I hope this point is clear to everyone. Let me extend it to like this. Yes, I hope that would be more sufficient. Okay, now the second number is what? 0F87. So 0F87 hex would equals to 0 0 means 4 times 0, F means 4 times 1, 8 means 1 triple 0, and 7 means 0 triple 1. So I'm going to exclusive OR. What is going to happen? Let's see. 0 0, and remember, exclusive OR, how it works. It works whenever we have two different inputs, it will always produce a 1. If you have similar inputs, it will produce 0. So 0 0 similar inputs, result will be 0. 0 0 similar inputs, 0 0 result will be 0. 1 0 result will become 1. Okay, next move to this 1 0 1 1 0 1 1 1 1 result, input are similar, so it is going to be 0 1. Okay, I hope you can do it yourself, so I'm just doing it. 1 1 and 0 0 1 1. So let's convert it into hexadecimal form. So it will be 1, it will be what? 1 2 12, 13. 13 is what? 13 is D, okay, and that is what? 3 plus 8 would be 11. 11 is what? B, and that is 3. I'm sorry for the noise, it is just very, it's a raining, so please don't mind it. I will try to reduce through processing, but let's hope you don't hear it. Okay, so it is hexadecimal and it's our expected result. Okay, so what is we are going to do? We are going to evaluate single step 1 2 3 4 is in AX, single step 0F87 is in DX, and remember the result will also coming in the DX, and that would be 1D B3. I hope this point is clear. Okay, in this slide we are going to deal with NOT gate, so we will be using only one operand. So let's use move, and let's say we move AX comma 2456 hex, okay, and we are going to NOT AX. So let's see, let's write in hexadecimal first, sorry, let's write in binary first. So 2546 hex is equal to what? 0010 0101 0100 and what? 6 would become what? 0110. Okay, I hope this is clear to everyone. So when we are going to apply this logical operation, it will become 1 1. I'm just going to invert it, it is not operation. 0 1 1 0 1 0, it would become what? 1011, and it would become what? 1001. So this is called 8 plus 4 12, 12 plus 13, 13 is what? D. 1010, that is A. 1011, that means 1 2 3, 3 plus 8 11, 11 is what? B. And 1001, that means 9. So that is going to be our result. Let me put this thing in comment. Yes, now let's press emulate button, so you can see this program is running without any error. Single step 2546 is loaded, and we are going to just revert it or not get it. So not X is going to execute as I press single step. I pressed it. Look, DAB9 as we were expecting. The result is clearly written here. I hope this point is clear. Okay, that's it from this lecture. I hope this lecture was easy because it is very simple. These are very simple logical gates, and we are just seeing their implementation in 8086 or 8088 microprocessor using this emulator. So I hope these are very easy, but if you have any question or query, you can note them down and we will try to resolve those queries in our online session. Thank you so much for listening.